Welcome to our deep dive into the fascinating world of the spectrum of light. In this video, we'll explore how light behaves when it passes through a prism, why we see rainbows, and what makes the sky blue. Whether you're a curious student or just love science, this journey will illuminate the mysteries behind the colors we see every day. Let's begin by understanding what the spectrum of light is and why it's so important in physics and our daily lives. Deviation produced by a prism depends on several key factors. First, the angle of incidence. As it increases, the deviation first decreases, reaches a minimum, and then increases again. Second, the material of the prism or its refractive index. A higher refractive index means greater deviation. Third, the angle of the prism itself. A larger angle leads to more deviation. Finally, the color or wavelength of light matters. Shorter wavelengths deviate more. These factors together determine how much the path of light bends as it passes through a prism. When white light enters a prism, each color bends by a different amount. The deviation increases as the wavelength decreases. This means violet light with the shortest wavelength bends the most, while red light with the longest wavelength bends the least. This property is fundamental to how prisms create rainbows and separate white light into its constituent colors. Dispersion is the phenomenon where white light splits into its constituent colors when it passes through a prism. This happens because each color travels at a different speed in the glass, causing them to refract at different angles. The result is a beautiful spectrum, just like the one you see in a rainbow. The cause of dispersion lies in the fact that different colors of light travel at different speeds in glass. When white light enters a prism, each color slows down by a different amount, causing them to bend at different angles. This separation starts at the first surface of the prism and continues as the light exits, resulting in a spread of colors. Let's visualize how white light gets dispersed by a prism. As white light enters the prism, each color bends differently due to varying speeds in glass. At the second surface, the colors separate even more, with violet deviating the most and red the least. This process creates a vivid spectrum, clearly visible on a screen placed after the prism. When a narrow beam of yellow monochromatic light passes through a prism, it simply bends without splitting. But if you replace it with white light, the prism splits it into a spectrum of colors. This difference is key to understanding how prisms reveal the hidden colors within white light. The speed of light in glass changes with wavelength. As the wavelength increases, the speed of light also increases. This means red light, which has a longer wavelength, travels faster in glass than blue or violet light. This difference in speed is what causes the colors to spread out when passing through a prism. Among the colors of white light, red travels the fastest in glass while blue travels the slowest. This is because the refractive index of glass is lower for red light and higher for blue light. This difference is crucial for the formation of the spectrum when white light passes through a prism. When a thin beam of white light passes through a prism and hits a screen, you see a beautiful band of colors, the spectrum. If you place a slit to allow only green light to pass, only green appears on the screen. This shows that the prism itself doesn't create colors, it simply separates the colors already present in white light. If a monochromatic beam of light passes through an equiangular prism at minimum deviation, the beam travels parallel to the base of the prism. When white light is used in the same way, it splits into its constituent colors, forming a spectrum. This demonstrates that white light is polychromatic, containing many colors. When white light passes through a prism and splits into a spectrum, it proves that white light is not a single color but a combination of many colors. This property is called being polychromatic. Each color in the spectrum has its own wavelength and unique properties. A spectrum is the colorful band you see on a screen when white light passes through a prism. It's made up of all the colors that combine to form white light. Each color in the spectrum corresponds to a different wavelength, and together, they create the vibrant display we associate with rainbows. The 7 colors of the spectrum in order are violet, indigo, blue, green, yellow, orange, and red. These colors do not all have the same width in the spectrum, some are wider than others. Violet is deviated the most while red is deviated the least, creating the classic rainbow order. Red and blue light have different wavelengths. Red is about 7.8 times 10 m, blue is about 4.8 times 10 m in vacuum. Both travel at the same speed, the speed of light. But in glass, red light travels faster than blue light, which is why they separate in a prism. A prism can split white light into its constituent colors, creating a spectrum. Interestingly, if you combine all the colors of the spectrum again, you get white light back. This shows that white light is a mixture of all visible colors, each with its own wavelength. The visible spectrum of white light ranges from about 4,000 angstroms to 8,000 or 400 nm to 800 nm. This range covers all the colors we can see, from violet at the short wavelength end to red at the long wavelength end. The color of light is a subjective property related to its wavelength. For example, blue light has an approximate wavelength of 4,800 while red light is around 8,000 Our eyes perceive these different wavelengths as different colors, making the world vibrant and colorful. Blue light has a shorter wavelength than green, yellow, orange, and red. This means blue light is at the higher frequency, lower wavelength end of the visible spectrum, while red is at the lower frequency, higher wavelength end. When white light hits the first surface of a prism, it experiences both deviation and dispersion. Deviation refers to the bending of the light path, while dispersion is the splitting of light into its constituent colors. Both effects are crucial for the formation of the spectrum. In the spectrum formed by a prism, red appears at the extreme end opposite to the base of the prism. This is because red light having the longest wavelength is deviated the least, while violet with the shortest wavelength is deviated the most. Let's calculate the frequency of yellow light with a wavelength of 550 nm. Using the formula frequency equals speed of light / wavelength, we get a frequency of 5.4 times 1014 Hz. This calculation helps us understand the relationship between wavelength and frequency in the electromagnetic spectrum. The frequency range of visible light is from 3.75 times 1014 Hz to 7.5 times 1014 Hz, corresponding to a wavelength range of 4000 A-ring to 8000 A-ring. This range includes all the colors we see in the visible spectrum. The electromagnetic spectrum includes many types of waves arranged by increasing frequency: infrared waves, visible light, ultraviolet, X-rays, and gamma rays. Gamma rays have the highest penetrating power, making them useful in medical treatments and scientific research. Arranging electromagnetic waves by increasing wavelength: gamma rays, X-rays, infrared rays, microwaves, and radio waves. Microwaves are especially important for satellite communication as they can travel long distances through the atmosphere. A wave with a wavelength of 0.01 A-ring is a gamma ray. Gamma rays are known for their strong penetrating power, which sets them apart from visible light. They are used in medical treatments and scientific investigations. X-rays are high-energy electromagnetic waves used to study crystal structures and detect bone fractures. Their wavelength ranges from 0.1 A-ring to 100 A-ring, making them ideal for penetrating materials and revealing hidden details. Let's look at the wavelength ranges of various electromagnetic waves. Gamma rays are shorter than 0.1 A-ring. X-rays range from 0.1 A-ring to 100 A-ring. Ultraviolet from 100 A-ring to 4000 A-ring. Visible light from 4000 A-ring to 8000 A-ring. Infrared from 8000 A-ring to 107 A-ring. Microwaves from 107 A-ring to 1011 A-ring, and radio waves are above 1011 A-ring. The electromagnetic waves visible to us have wavelengths from 4000 A-ring to 8000 A-ring. This range includes all the colors of the rainbow from violet to red and is the only part of the spectrum our eyes can detect naturally. Beyond the red end of the visible spectrum lies infrared radiation, and beyond the violet end lies ultraviolet radiation. These regions are invisible to the human eye but play important roles in technology and nature. The invisible spectrum refers to the parts of the electromagnetic spectrum beyond the red and violet ends of visible light. We can detect these radiations using special experiments, like observing chemical changes in silver chloride for ultraviolet or temperature rise for infrared. Ultraviolet rays have wavelengths from 100 A-ring to 4000 A-ring, visible light from 4000 A-ring to 8000 A-ring, and infrared from 8000 A-ring to 107 A-ring. Each region has unique properties and uses, from sterilization to remote controls. Radiations with wavelengths longer than 8 times 10 m are infrared, while those shorter than 4 times 10 m are ultraviolet. These boundaries help us classify electromagnetic waves and understand their effects. X-rays and ultraviolet rays have frequencies greater than violet light. X-rays are used for studying atomic arrangements in crystals, while ultraviolet rays help detect the purity of gems and other substances. Microwaves are used for satellite communication, ultraviolet for detecting purity, infrared for remote controls, and gamma rays for killing cancer cells. Each type of electromagnetic wave has unique applications based on its properties. Ultraviolet radiations travel in straight lines at the speed of light, obey the laws of reflection and refraction, and affect photographic plates. However, they also cause fluorescence and can be hazardous to health. Infrared radiations, like visible light, travel in straight lines and at the speed of light in vacuum. They obey reflection and refraction, but unlike visible light, they are invisible and do not affect photographic film. Infrared radiations are used for photography in fog, as signals during war, and in darkrooms because they don't affect photographic film. Rock salt prisms are used for infrared spectra, while quartz prisms are needed for ultraviolet since glass absorbs these radiations. Scattering occurs when sunlight enters Earth's atmosphere and is spread in all directions by dust, water, and gas molecules. This process is responsible for many natural phenomena, including the blue color of the sky. The intensity of scattered light is inversely proportional to the fourth power of its wavelength. This means shorter wavelengths, like blue and violet, are scattered much more than longer wavelengths like red. This effect is most noticeable when the scattering particles are much smaller than the wavelength of light. Red light is used for danger signals because it has the longest wavelength and is scattered the least by air molecules. This allows red signals to be seen from the greatest distance, making them ideal for warnings and alerts. From the surface of the moon or in space, the sky appears black. This is because there is no atmosphere to scatter sunlight, so only direct sunlight is visible and the rest of the sky remains dark. The blue color of the sky is due to the scattering property of light. Blue light, having a shorter wavelength, is scattered more by air molecules than red light. This scattered blue light reaches our eyes from all directions, making the sky appear blue. At sunrise and sunset, sunlight travels through a longer path in the atmosphere. Blue light is scattered away, leaving mostly red and orange hues to reach our eyes. That's why the sun looks red during these times. At noon, the sun is overhead and light travels a shorter path through the atmosphere, resulting in less scattering and a white sky. Clouds appear white because they contain water droplets and dust particles larger than the wavelength of light, scattering all colors equally.